We'll hit the record button. So then everything is being captured. So yes, we have homework 5 finished yesterday. Your grade should be available. Let me know if you have questions about anything that you missed, or if you think there's an answer key problem. I'll be happy to check on that for you. Your next thing to do is formative assessment number 6, which is available inside Icon due Monday night. And note that I have posted on Tuesday's class a formative assessment 6 starter kit designed to help you figure out what I'm asking when I say write an equation or write a programming statement. This is like the parts that you would fill in to do this. So I would like you to still do it in Icon, but you can use this as sort of a structure for what your answers should be like. And I'm happy if you copy and paste the stuff directly into Icon. That's totally fine with me. Your last homework is available. It will be due at the end of finals week. So you got 2 weeks and a day to work on that. And like I said just a second ago, I am hopeful that by the end of today, we will have covered everything that you would need to do homework 6. And I have one more lecture that I need to put together that doesn't have a corresponding example, but I'm kind of waiting to see how far we get as to how much time I'm going to have to do that. So I will let you know when that last piece of materials is available to you. So any questions about schedule, logistics, outstanding coursework? Nope. Okay, so 5:00 p.m. at the end of finals week, that's when everything's going to be due, and I'm going to turn in grades shortly thereafter. So if you're missing an assignment or a formative assessment, this would be a great time to get caught up so that you can get all the points possible to go into your final tally. But for now, we have an example that we get to start. Practice with main effects models and then introducing some interaction terms. Are we ready to dive in? Maybe? Yeah, our last example, example 5. It actually starts with the exact same model that we left off with in the example 4b. So this is the story of the fake old people data, 550 older adults predicting cognition as an outcome from age, grip strength in pounds, sex, and dementia group status, where it's a 3-group variable. And what I wanted to demonstrate with this model again here is how one would go about getting predicted values that you could go and make a plot, and then how to make plots. So this is a little extra piece of something that I want you to have for your future reference. And I note that online, I have additional syntax that's not in the handout for computing effect sizes because it's not different than what we've already done. But I had to decide like what to focus on for. This is already 24 pages long, so there's not really any effect sizes in this handout. That is to say that they're still important. I just had to cut back a little bit in how much we would cover. So this is focusing on the idea of main effects becoming conditional main effects in the presence of interaction terms. All right, so in terms of the setup to import the data and to create the predictor variables that we need, this is exactly the same as it was in example 4b. There's nothing that's been changed. So I have it in here for completeness. That way each example can kind of stand alone, but you've seen all of these things. So for instance, in your homework, I'm asking you to center 2 continuous predictors at known constants. There is a binary predictor that you can turn into a 0-1 variable. So if it's binary, then you only need one difference. And so there's not a lot of coding involved in that. But we've got examples of how to do all of that kind of stuff in each of the 3 programs. Is there anything that you want me to go over again with respect to making new variables, or do you feel reasonably good about this part?
Will you share your screen?
Oh, that would be brilliant, wouldn't it? Thank you for saying something. Yes, I will. Now I'll rephrase the question. Is there any part of this that you'd like me to go over again or differently with respect to importing data or making variables? Now I'm making sure I'm recording too, because I don't trust myself. Okay, there we go. No, good with this? Okay. Then here is our first model. So analogous to section 1 of your last homework here, we are putting in, I'm going to call these things main effects. So switching terminology a little bit given the context of what's to come. When you have one slope that is multiplying a predictor variable, and that predictor variable is not included in any other interaction terms, then this slope The terminology for that, unique marginal. So each of these slopes in this model is describing the unique effect of that predictor on the cognition outcome after controlling for what the predictor has in common with all the other predictors. So what does age contribute to cognition that grip strength doesn't, that sex doesn't, that dementia group doesn't? So when I talk about what beta 1 means, for instance, it's going to be the change in cognition per year of age, period, because it's unconditional marginal in this model. That is going to change as we add terms to the model that render these slopes conditional instead. So we are assuming a linear effect of age, a linear effect of grip strength. Both of these are quantitative variables. Numbers are numbers. I have a linear effect of gender, which in this case is just a binary variable. So men are coded the 0 and women are coded the 1. I have chosen to use indicator coding for my dementia group variable. So my contrasts here are going to give me how future differs from none and how current differs from none. So none is the common base point for both of these things. And just to remind you that if I want to know what the difference is between the non-reference groups, future and current, I've got the math to do that here. So this part right here tells me how the model predicts the mean for the current group. It's the intercept of what it would be for the none group as a reference, plus this term right here. Likewise, how the model predicts what the outcome is supposed to be for the future group is what it is for none, plus the difference for future right here is the 1 group. So if I take what it is for current and subtract what it is for future, then this linear combination of the two slopes gives me the difference between the future and current groups. So it's in the model implied, even if it's not directly given. So you've seen this before, but just reminding you of the logic of how to form linear combinations. So we've got then Proc GLM and SAS to start with. Got all my centered predictors lined up here. My contrast statement, you got to practice this in your last homework, but just to remind us, a contrast type statement is necessary anytime you want a hypothesis test that involves more than one slope at the same time. So in this context right here, what I'm asking for is to lump the two slopes together that refer to dementia group so that I can get an overall test of whether there are any group differences. In ANOVA language, this is what's known as an omnibus main effective group. So there's 3 groups, which means there's 3 possible differences. That means it's a 2 degree of freedom test. 2 slopes create the 3 possible differences. I'm also using an estimate statement then to get the linear combination of one slope minus the other that will tell me how the future group and the current group differ from each other. So estimate is used for linear combinations that create one new slope. Contrast is used for when you want to have more than one slope tested at the same time. So they're 2 different purposes. Still saying in SAS, these estimate statements right here demonstrate the long way of requesting predicted outcomes for prototypical kinds of people. So this would give you the points that you could potentially put in a figure that shows what your model is predicting with your data. And the values that you would use are based on the context of each variable and what a meaningful value would be for low, middle, and high. So given the distribution of age, I chose 80 as my low value. So age is centered at 85, so I put -5 here because it's centered age that I'm filling in these values for. 0 for age 85 and +5 for age 90. Likewise, low, medium, and high on grip strength, I went with plus or minus 1 standard deviation roughly. So a standard deviation on grip strength was 3. So an example low value of grip strength would be 6. A middle value would be 9, which is near its mean, and a relatively high value would be 12. And so then I have 9 possible outcomes here, 1 for each combination of low, middle, and high for age and grip strength. And I have chosen to take my other 3 variables and hold them equal to 0. So the picture that I'm intending to make is not designed to illustrate the effects of dementia group or gender. I'm holding them constant instead. And by holding them constant at 0, more specifically, I'm developing predictions for a man, because that's when sex is coded 0, who never will have dementia for the none group, when both of the dementia slopes are 0 as well. So this is the long way, because this is a lot of typing. And if you wanted to change who the prediction is for, you'd have to change these values in here as well. So this can be somewhat tedious and error prone, but it's also very transparent as to what you're doing. So what I did was save the table that is being created right here as a SAS data set. I then went into the table and carved up the labels for these things into separate variables so that I could then use those in a plot. So the plot that is being created will show up in just a second. So here's my model. Reviewing concepts then, what is this part telling me? Model sums of squares, error sums of squares, dividing by degrees of freedom to get mean squares, and then ultimately dividing those to get my F. What's this box telling me on the whole?
The total effect.
The what?
The total effect of all of the, like the predictor and the interactions.
Yeah, it's telling me whether or not my model is significant as a whole. So lumping together all 5 slopes, do they significantly predict cognition together? Yes, is the answer. How well did they do? What do I need to look at to answer that question?
R-squared.
Yeah, that's the next little piece in SAS here, R-square. They got 28% of all the variance in cognition. So I can talk about that R-square of 0.277 in a couple different ways. One is explained variance. So it's 27% explained. And let's do the math in my head. Always dangerous. 73% unexplained? Does that sound right?
Mm-hmm.
Yeah. Another way to think about it is relative to the empty model with no slopes in it, my residual variance has been reduced by 27%. So the change in my mean square error term relative to what it would be in the empty model. And I can also talk about my R-square as the square of the correlation between Y, which is cognition, and Y hat, the cognition that's predicted from my slopes. So that is a more R-ish interpretation relative to explained variance and proportions and such. So this is kind of like the big picture, does my model work and how well does it work? Then we dive into the specifics. So my contrast here tells me that yes, there are significant mean differences across my 3 dementia groups. The F for that is also significant. And then more specifically, I can look at each individual estimate. So my intercept is for the predicted cognition when all my predictors are 0, right? That's always what an intercept is. So 29 is the cognition score for an 85-year-old who can squeeze 9 pounds, who is a man, who is never going to have dementia. And then each of these, in this model, these are just regular old slopes, but I'm going to call them main effects, because it's the idea that each of these slopes is pertaining to one variable, and each variable's effect is carried just by that one slope. It means that that slope operates equally for everyone. So the slope for age, for instance, minus 0.4, that is a unique marginal effect, marginal unconditional being synonyms. Cognition is predicted to be lower by 0.4 per year of age for everyone, because age is not involved in any other of these terms. Likewise, cognition is predicted to be higher by 0.6 per pound of grip strength for everyone. Who are lower, men or women? This is a negative slope for gender. Men are 0, women are 1. Who's lower? Men are 0, women are the 1, and the slope is negative.
So men
Say it again. In this case, it's the women.
are, okay.
Yep, because when you have a 0, 1 variable, the slope tells you how the 1 group differs from the 0 group. So the women get the coefficient multiplied by their score, which makes them lower because the slope is lower. So more directly, women are lower than men on average by 3.65, 66, what have you. Likewise, both of these slopes for dementia group are significantly negative, meaning that the 1 group in each of these contrasts is significantly lower than the 0 group. So the 1 group is future or current in each of these lines, significantly lower than none. Then we get our difference between the future and none groups. That's the difference of those two slopes right there. They differ by -10. So that tells me that the current group is lower than the future group by -10. And the rest of these are my predictions. And I throw those into the plot, and this is what it looks like. So this is what we looked at on, I think, Tuesday. And we talked about the idea that these lines are parallel because this model does not have any moderation in it that says the effective age depends on grip strength or that the effective grip strength depends on age. That's why the lines are parallel. So the slope of these lines, given that the x-axis is grip strength, is describing how grip predicts cognition. Each separate line is for a different age, and the vertical distance between the lines is conveying the slope for age. The people at the top are the youngest people, because age has a negative slope. So the people at the bottom are the oldest people. Okay. How are we doing so far? Reasonably okay? So here's an alternative to doing all of this typing. In SAS, this is my hack. Fake people. Now, this is not something that you will necessarily need to do for your homework, but it's a hack that I want you to have for your lives, okay? So I am creating a new empty data set in the work library, and I'm calling my data set fake people, because that's what I'm making here. The input statement lists the columns that I'm going to put into my data set. I recycled my code to center the predictors from before. And then after the keyword data lines, I am entering rows of data. So I have given all of my fake people, the first variable here is person ID, a value of -99 so that I know when I look at it who's fake and who's not. I have given them my values of age, 80, 85, and 90, and then my 3 possibilities for low, medium, high on grip strength, and I've held the rest at 0. And then down here, I'm merging my fake people into my real people. So the fact that I have not given them an outcome is why this is okay. They don't have cognition, so they are not going to contribute to the estimation of the model. They're not going to mess anything up. But what's going to happen is that on this output statement here, so I'm rerunning the model and adding this command, it's going to create a new data set in the work library, and I've named that data set pred main outcomes. And I have added a column that I called y hat, and a second column that I've called SE for y hat. So in my new data set, all of my cases are going to get predicted outcomes, including the fake people. So I can go into that data set, borrow those points, and throw them into Excel or my favorite, whatever plotting software I want to use, including SAS. So it's a lot easier to make up one data set of fake people and have the model create predicted outcomes for it than it is to write out the model, essentially, in this form, where you'd have to have one separate row for every possible predicted outcome that you want to create. So I do this in SAS, and I've done this in SPSS as well. The other 2 packages have better ways to do it. All right. Questions so far? All right, data folks. Same model, same linear combination. reviewing test statements. This was the new thing that was in your last homework. Test is the analog to contrast. It's used to lump together slopes. So when you want a joint hypothesis test of more than one slope, such as to get the omnibus main effect of dementia. So the slopes are put in parentheses and each is set equal to 0. LinCom is to get linear combinations to create one new slope out of existing slopes. And you've seen that one before. This one used to get the model implied difference between the non-reference groups. And for those of you who like typing, this is the long way to get predicted outcomes. Yeah, shaking your heads. We don't like typing, do we? Not especially. But this has the advantage of being very transparent. So I am creating predicted outcomes for the same combinations of 80, 85, and 90 by grip strength 6, 9, or 12. So I've got 9 lines here, and I have the underscore constant as the intercept. I need one of those. I need the slope of age times the value of age I want the prediction for, the slope of grip times the value of grip I want the prediction for, and I'm holding the other variables constant at 0. So here's my Stata output. The first 2 tables in SAS are condensed into one big table in Stata, but it has the same information. So 88 is my residual variance left over. My R-square is the 0.27. The F for the model tells me that my slopes do work together to significantly predict cognition, and they do so with an R-square of 0.27. Here's all my slopes. Intercept is always last. The new test statement that tells me, yes, there are significant differences across my 3 dementia groups. And my model implied difference between future and current. And then we get to all the separate LinCom statements that I did lots of typing for to get predicted values. And I printed 3 of those and called it good. Here's the faster way. This one line right here, Stata users, this is why you're Stata users in part. This is a brilliant command. Margins. That line writes 9 lines, and it can write even more if you wanted to. So margins is used in Stata in a lot of different contexts. What it's doing here is creating predicted outcomes. So the at command says, for what values of the predictors would you like an outcome for? Okay, I'd like age. And the way to read this, start at -5, in increments of 5 inside the parentheses, up to 5. So from, by, to. So it's going to give me 3 possible values of ages, -5, 0, and 5. It's going to give me 3 possible values of grip for -3, 0, and 3, and hold the others constant. And then it understands that you probably want a picture. So margins plot then requires you to tell it which variable do you want as your x-axis, and it will do the rest for you. It also allows you to name them so that you can refer to them in your code. And this is the picture that made. Nice, happy little picture with error bars already included. Still parallel lines, though. And here are the predictions themselves that this one line of code generates. So super slick. All right. Any questions on Stata? Pictures, predictions, etc.? All right, R, folks. Same principle for you. There's the long way and a short way. So here is my formula that tells me the order in which my fixed effects are listed that I then need to know in order to get the correct order. Oh, sorry. Getting a little mouse happy here. Come back. The correct order in these statements. So that order and that order are the same. So you've seen most of this before. Here is my GLHT to test multiple slopes. So there's different forms of GLHT. This one is used to lump together multiple slopes, just like contrast in SAS or test in Stata. And this version is used to get one at a time. So the numbers that go in the GLHT parentheses. Stop that. Goodness. The first thing is a 1. What's that thing meant to represent? That's my fixed intercept. So in all of my predictions, there's a 1 in the first spot because all my predicted outcomes start with an intercept at a minimum. Then minus 5 here goes there because the next thing that I typed was age. So if I type this in a different order, then this would be wrong. They have to match. So age gets the plus or minus 5, grip strength gets the plus or minus 3, and then the other 3 fixed effects are all being held at 0. So this is the long way. Here's the output from the model. Here's the analysis of variance table we ignore except for this one number that gives us the residual variance. Here's the solution table that we're used to seeing for the intercept and the slopes. And the summary of what happened with respect to the model is at the bottom. So it gives you the square root of the residual variance as residual standard error. It tells you your denominator degrees of freedom, tells you your R-square, and then your F-test for the model, which is the same thing that the other programs give as well. So a slightly different way of presenting it, but the same stuff. The general linear hypothesis test for both dementia slopes then tells us that overall there is a significant difference in the outcome across the 3 groups. Here's the missing group difference that we didn't already have. And then here are the predicted outcomes from our multiple GLHT statements. And here's a shorter way. So there is a package called Prediction that I downloaded. It's one of the packages that gets downloaded and loaded in your R code. And it operates like Stata margins. So this part right here, the at command, that is writing 9 separate GLHT statements in the same way that it does in Stata. So I'm holding some of the predictors constant at 0, and then grip 9, I am starting at minus 3, going up to 3 in increments of 3. Starting for age at minus 5, up to 5 in increments of 5. And so then it gives me, if you ask for a summary of this prediction, by the way, it doesn't give you all of this if you don't ask for the summary, but once you add the summary, then it spits out this nice, happy little table. And I had put the wrong version of the picture in here in the handout, but I fixed it. We get the same picture with the parallel lines. In here is the plot code that created that picture. So less typing if you use prediction, but potentially less transparency as well. Okay. Any questions on getting predicted values? Or interpreting slopes outside of interaction terms like usual? Okay, this is section 1 of your last homework. Ready for section 2? Why not, right? We're here.
I just had a quick question about this.
Yeah, go ahead.
So in the R there is the sex MW, so men and women.
Mm-hmm.
But like in that C with the brackets, I was just confused as to why do we put like zeros for all? What does that signify?
For these?
No, the one on top.
Oh, the one on top.
More like the code before this.
Code before this.
Yeah, this one.
These? So these 3 zeros signify the same thing as these zeros here. It's just now these are attached to the variables they represent, so it's more explicit. But what I'm doing is asking for low, medium, and high values of age and grip, and I'm holding gender and dementia group constant at 0 because they're not going to be part of my story right now. And so these then make it so that those slopes do not contribute to the predicted outcome.
My only question was that because then we put, like you said, we put women as 1 and men as 0.
Mm-hmm.
Wouldn't that count as counting only men?
Yes.
At 0?
Yeah, this is a prediction for a man who does not have dementia.
Oh, so if it's for a woman, then it'll be all ones.
That's correct. Yep, I'm holding it constant because I'm not trying to show the impact of that source of variability right now. But if I wanted to hold it constant at something else, I certainly could do that.
Oh, got it. Sorry, I think I missed that part on the men.
Yeah, so constant is the key idea. Unless I wanted to show like multiple plots where I showed the effect of gender in some and age in some, and like I could do that, but that's not what I'm trying to do at the moment. Yep. Yep. In this coding scheme, by the way, I would never have something that looks like that with ones in both places, because this is indicator coding in which you can only be in one group or not the other. So there's nobody who's in both the future group and the current group in dementia. So it will give me a number, but that number will not mean anything. So it's up to you to put in values that make sense. And R does give you a warning if you try to come up with values that are outside the range of the data, but will still give you the numbers. Okay. Other questions on code or concepts? No? Ready for some new stuff? Interaction terms, moderation. So I have syntax and output, I think, let me see what I have here. I had all of the packages. Yep. I went syntax first, output second, but I've got it in all the packages because this is what you need for homework 6. So there's your me not being subtle. This one for homework 6. So the structure of this is analogous to what you'll be doing in homework. So I've added 2 new effects to my model. So I've left everything in that was there before, and I've added interaction terms between my binary gender variable and my quantitative age variable as one. So I've got this new beta 6, and I did the same thing with gender as a binary variable and grip as a quantitative variable, their interaction, and I'm calling that beta 7. So 2 new terms here that conceptually, what am I asking? What are the ideas that go underneath these new interaction terms? Any guesses?
You're doing like a comparison of both the of the sex.
Say that again?
That you want to do like you're doing an interaction of the comparison of both the variables rather than just one.
I am doing an interaction of sex with both variables. That is true.
So is it the interaction of both of those variables on cognition?
Yes, it is. So yes, input in the chat window, how sex and age interact and how sex and grip interact, that is all true. But conceptually, what does it mean if they do? That's what I'm after. Let me do one for you. So if beta 6 adds significantly to the model, what that means is that the effect of age depends on whether you're a man or a woman. It means that there is a difference in the age slope as you transition from men to women. So this is going to be the increment to the age slope in the non-reference group of women. So do people need different age slopes as a function of their binary gender? Is this one? How about that one?
Grip change if you're a man or a woman?
Does the effect of grip change if you're a man or a woman? Yeah. So we are allowing the extent to which grip strength predicts cognition to vary as a function of gender. Yep. And I can also spin it the other way. The other way is to think about gender as the variable I care about and age and grip as the moderators. So we just found out in the previous model that women were worse by like 3 points, right? Do you think that that gender gap depends on how old you are?
Seems so.
Probably, yeah. Do you think it depends on how strong you are?
Yeah.
Could. So we can look at it either way. But the core idea is that we're asking whether or not the slopes of these variables depend on the value of the variable that it interacts with. Moderation is the idea here. moderation of gender differences by age and grip, also moderation of the slopes of age and grip by gender. So relative to the previous model that only had these main effect slopes in it of each variable all by itself, we're adding these two new interaction terms where the asterisk denotes their interaction in SAS. So this is a context in which if I wanted to know if the model got better, I'm going to have to ask for a test of that. That's going to be my contrast right here. So note that I have two different contrasts. This is the one that pertains to the change in the R-square. So just like you did in your previous homework, anytime you add more than one slope at a time to a model, you don't necessarily know if the change in R-square that results is because of one slope or the other, or the third or the fourth, or however many you have. So this is asking the question, do these two slopes work together to significantly increase the R-square, significantly improve the amount of variability accounted for by the model? This is what's also known as hierarchical regression in some contexts, because we're starting with slopes and adding them in chunks as a hierarchy. So this contrast is going to tell me whether or not my two new interaction terms significantly help the model. The contrast I already had is still going to talk about dementia group after controlling for everything else, and then this one is going to give me the missing group difference from before. So these are not different than what we had to begin with. So up to this point, nothing new in terms of the code until now. So if I want to request what the age slope would be as a function of gender, here's my process. Go up to the model, find all the things that have age in it, because I care about the age slope. So do I need beta 0? Does it have age in it? Nope. Do I need this one? Yes. Do I need this one? No. This one? No. 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 Do I need this one?
No.
No. This one doesn't. Tricked you. You are paying attention. I knew it. So yeah, all we need are these two things. So the estimate type statement that I'm going to write to get the slope of age can only have age in it. Otherwise, it's not going to work. So step 1, find all the stuff that has the slope of interest. We're talking about age, needs to have age. Here we go. Step 2, factor out age, because that's the variable we want the slope for. So I pull age out of this part here, and I pull age out of this part right here, and I'm left with the thing that's in brackets. That is my age slope according to the model. Beta 1 plus beta 6 interaction term times sex. Those are my ingredients to write the programming statement that goes with this age slope for any gender. So in your formative assessment, I said write the equation for and then write a programming statement for. This is what I'm talking about. Equation for would be this chunk right here in the brackets. How does the model tell me what the age slope would be for any value of the moderator of gender? Then how do I ask for that? Well, in this story problem, gender is binary, so there's only two possibilities. The model gives me an age slope for men, and it also gives me a model implied age slope for women. So both of these programming statements start out with age and 1, because at a minimum, the age slope is beta 1. At a minimum. Then the question is, what else do I need? Well, if I'm trying to predict what the model says the age slope for men should be, then I go over here, and if it's a man, this variable is 0. So this part actually drops. And that's written here explicitly. I don't have to type it, but I'm doing it on purpose to show you how the structure of it is. So I don't even really need to ask. Beta 1 all by itself is the age slope for men, because that's when the interaction term would drop out, when it's zeroed out. The one that I do need to ask for that's not directly given, but that is implied, is what it is for women. So now I need 1 beta 1, and if it's for women, then my sex variable is 1, so that's what goes after the interaction term instead, because that's what would go in the parentheses right here if it's for women. So how the model says the age slope should be for women is beta 1 plus the interaction term beta 6, linear combination. If I wanted to know if the age slope differs between men and women, I would take this line and subtract that line. If I do that, the main effective age cancels, and all that's left is the interaction term, because that's what it means. The interaction term directly tells you how the age slope for women differs from the age slope for men as the reference. Interaction terms are slope differences, always. Okay, how are we doing with that so far? So far, so good? Now let's change the story. What if I want to know about grip strength? Here's my process. Go up to the equation, find all the terms that have grip in them. How many do I need? There's just 2. Yep. Grip all by itself, which stands to reason if I want the grip slope that should be involved. But the only other thing that's involved is right here. Those are my ingredients. Same process. Get all the stuff that has the slope of interest, which is grip, factor it out. What's left in front of it, in the brackets, is how the model says the grip strength slope is constructed for any gender. So now the first thing I type is grip, because I need one of those, because at a minimum I need beta 2. Beta 2's grip strength slope is only for men, because that's when the other part would drop out, is when gender is 0. So to get what it is for women, I'd throw a 1 in here, and that's why a 1 goes right here. So in your last homework, you will have a similarly constructed model with a binary predictor interacting with the quantitative predictor. The variables are different, but the structure is exactly the same. Now, if I like typing, and I want to show the effects of my interaction terms, I could generate predicted values for various kinds of people. Here I'm sticking with low and high for age and grip strength for men, and low and high for age and grip strength for women. So what I'm writing with these statements is y hat, predicted outcomes. So that's why everything goes in here, because everything in the model contributes to the predicted outcome. Anything that's not written here, like gender and dementia groups, are explicitly held to 0. So these predictions are all for men without dementia because I've left them out. So the intercept is in all of these lines, because at a minimum, a predicted outcome needs the intercept. Then the values that show up after the variables are what value of the predictor I want the predicted outcome for. So these are all 0s and these turn to 1s, which mean the first 4 lines are going to be for men. The second 4 lines are going to be for women. Then I've got low, low, high, high for age, low, low, high, high, low, high, low, high, low, high, low, high. So I've got all the combinations. And then note the interaction terms are part of the story. So why do you think the first 4 lines here are all zeroed out for all the interaction terms?
Because men are already like who are seeing the information for just with the
Yep, because these are predictions for men,
Yeah.
and men are the 0. So men are the 0. They stay 0. Doesn't matter what grip and age are. Likewise, down here, these interactions are, say, -5 and -3, because they're multiplied by 1. So 1 times -5 is -5. 1 times -3 is -3. And then I have my code to make pictures, and those will show up later. Okay, so any questions on SAS syntax? Okay, let's do it again. This time in Stata. For homework 6. So in Stata, interaction terms, note that I have 3 lines here and a note that says line continuer. In older versions of Stata, you have to tell it to keep reading if you return to a different physical line of code. They've apparently done away with that in newer versions, but I want my code to be backwards compatible, so I'm putting it in here. So if you forget this, it will ignore all of this because it doesn't understand that it's all one command. So here are my 2 new interaction terms. To denote the interaction, it's a hashtag or a £, depending on how old you are. Here's my new test statement that is lumping those 2 new interaction terms together. That's going to tell me whether the increase in R² they create is significant, whether those 2 new interactions work together to significantly improve the extent of prediction. Then we get to how the model gives us age slopes for any gender and grip strength slopes for any gender. So this part is exactly the same as what we just did. The only difference is how I tell that to Stata. And in this case, it's actually more explicit. It matches the equation. So I need 1 beta 1. That's this part right here. Then I add to it, literally add to it, the value of sex that I want the prediction for. And in this case, I want it for a dude, so that's a times 0. And in this case, I want it for, let's go, what's the opposite of dude? Chick? I'm trying to vary my language, right? Dudes and chicks. I think those are both similarly offensive. Let's go with that. Times 1 here. So do you have to write times 1? You do not. If you don't write times 1, it knows what you meant. Why do I write times 1? Because then it matches the code in the other packages. So that's why I write it. I'd rather be transparent sometimes than fast. Same thing for grip strength. Then we need the slope of grip plus how gender moderates it. 0 for men, 1 for women. And then here's the short way of asking for predicted outcomes. Note that all you have to do, even though there's interaction terms in the model, is tell it what predictor values you want the predictions for, and it understands how to make the predicted outcomes. So you don't have to do anything special if the predictors that you're going to plot are part of interaction terms or not. It will handle that for you. So here I'm starting at -5 in increments of 10 up to 5. So that's just -5 or 5. And this is going to give me -3 or 3 because I'm in increments of 6. And gender is starting at 0 in increments of 1 up to 1. And the others are being held equal. And then we get our pictures. Okay. Stata users, any questions on this syntax? Last but not least, R. So one thing to watch for, the other packages do not care if you write the interaction terms one way versus another. So I could write age times sex or sex times age, and Stata and SAS are like, cool, whatever, I knew what you meant. R's like, nope. You'd write it my way, pal. You're in my world now. So because I wrote age first, it has to be this way. Otherwise, it will yell at you. If I had written sex first, it would have to be the other way. And it's a colon to denote the interaction term. I don't know if you've seen those yet or not. Have we seen that? Okay, yeah, it was squared before, which looked different. but it's a colon. The other thing to watch out for that I learned the hard way is that sometimes when I write these out, I like to have all of the terms that go together right next to each other. So like if I took this interaction term and I wanted to put it like next, so like I wanted to do it that way, R will let you estimate the model, but then it reorders the fixed effects in the order that it wants, which is always to put the interaction terms last. So why that matters is that the order that you wrote is not the order internally that it's using. All of these values are tied to what it's using. So you cannot stick your interaction terms in the middle of your list of main effects without having it screw up what these coefficients mean down here. So recapping, in R, all the main effects come first, then the interaction terms in the order in which the main effects were listed initially. Age and grip were listed before sex, and that's why they have to be written this way. Okay. Here's my new analog to contrast and test that gives me the joint test of my two new interaction terms against 0. See whether they've significantly improved model R squared. And here are my simple slopes. I know. Scoot up just a scooch. There we go. So age slope for men, let's break this down. That first 0 refers to the intercept. We don't need an intercept if we're making an age slope. The first 1 right here refers to the slope of age. We do need that. We don't need the slope of grip. We don't need the slope of gender. We don't need the slope of dementia future. We don't need the slope of dementia current. Then the only possible values that would be relevant is the second one here, because that's where age and sex interact. So this one is 0, and this one is 1, because that's where you stick the interaction term for what the moderator value is. I'm asking for the age slope for men, which is why the first one is 0. I'm asking for the age slope for women, which is why the second one is 1. Likewise, in the last 2 lines, I'm asking for the grip strength slope instead. So these ones go with the main effect of grip. The grip by gender interaction is last. The first one is a 0 because that one's for men. The second one is a 1 because that one's for women. So you have to tell it what to do with the rest of the coefficients in the model. And if you say make them 0, that means leave them out. All right. How are we doing? Isn't R fun?
I'm not excited to make that.
I'm not excited to make that either. It gets much worse because like this is not even that complicated of a model.
Right.
Like you could imagine just like a row of like a whole bunch of 0s and 1s, and it's like you're living in the Matrix or something.
No.
And
It's
yeah,
really easy to make a mistake.
it is. It's super easy, and ours like, okay, I don't know why you asked for that, but here's your
But
estimate.
Sure, right.
Yeah,
right.
I'll make it for you.
And then it just stays on your mind till you correct it, and then there's one error and you can't figure it out, and then you find out that there's like 1 0 or 1 here and there.
Yep. Yeah, no, this sucks. Like
I have
this
nightmares
is
about this.
terrible human factors right here is what this is.
But it's very satisfying to get the answers also. at
True.
the end.
It is satisfying, but in your lives you won't have green boxes.
That, you're right.
Yeah, so that's a common question I get about this point in the semester. It's like, but what am I going to do when I don't know what the right answer is supposed to be?
Right.
Well, this is where you can get your calculator out. Because if you know that, like conceptually, that what you're supposed to end up with is this number on your output plus this number, then you can get your calculator out and see what it should be.
Mm.
And if the number you get back matches what you think it should be, then you wrote this statement correctly. So honestly,
Yeah.
that's one approach, because these statements are used to not just get the linear combination estimate, but more importantly to get its standard error and hypothesis test, because the standard errors you can't just add together or subtract in the same way. Each of these coefficients has a covariance to its standard errors that has to show up as part of the formula. And I've sort of hidden that from you because learning it is not worth the time it would take, because we don't do math by hand.
Right.
Like, if you've learned nothing else in this course, like, learn that. Like, we let the computers do it for you. They're better, they're faster, they know what the formulas should be, and they will get it right, as long as you give them the right information. The other thing, though, that I was taught, like I said, I did not learn this as a concept, this idea of asking for linear combinations, until I was on the tenure track. I did not learn this at all. And when I finally did learn it from somebody, I was like, oh my God, why didn't I know this? What I learned was to hack the model. So think of it this way. Given this interaction term, this slope for the main effective age is going to be for men specifically, because they're the 0. If I wanted to know what it could be for women instead, and I didn't know how to do any of this 0-1 stuff, I change the coding of gender. I make women the 0. And now this is for women instead. That's how I learned how to do this. And that's not wrong. It's just labor intensive to rearrange your parameters to get one new thing and rerun the same model multiple times. But that is another way that you can hack it. So when I'm in a situation like for my longitudinal class, I remember building an example where we were up to like 3-way interactions, and I wasn't sure that I got my coding right. I hacked it by changing the reference groups and seeing if the estimates I got back were now for the new reference group, and that's how I knew if I was right. So it is tricky.
Yeah.
It can be very tricky. All right. So is this plotting code, by the way. R is great at making pictures. You only have to type all of this. And no, I did not do this. Jonathan did this. He helped me. He didn't type it. He told me what to type.
Okay.
No, he did not build this, but he told me at the beginning of this, like, if you're going to learn R, just ask me. Like, don't ask the Google. So I'm like, send him a type message. How do I make a plot in R? Okay, I'll come over.
Where does he learn? Where does he learn it?
So Jonathan is my husband, Jonathan Templin, the E.F. Lindquist chair of our program. He learned R like a million years ago and went away from it when it sucked. And then when R Studio was invented, he went back to it. No, he's super good at R, and he's super good at coding stuff in general. What he does in terms of quantitative methods is write algorithms. So he develops new measurement models, and he writes the software to estimate them himself. Like, he's that kind. Like, he owns 2 patents. Like people have paid money to patent his software, and he licenses it to people and stuff. Like, he's of that kind. So that's why I'm like, can you help me make a picture? And he's like,
Right. Simple.
oh, you're so cute. Look at that. You want a picture? Like, well, I can't write algorithms, but I made a picture, though. I did get it to work eventually. But anywho, hating on R. It's free, but you got to type all this.
Right,
So
right.
I'm not sure that free is better. But anywho, here's what we get. So we have output in each of the programs, I think. Yes, I did, because I knew that you would need this for your homework. So new stuff, not really. The first table in SAS is still telling us about the model as a whole. And I have noted here manually the change in the R-square that resulted after adding in our 2 new interaction terms. It improved by 0.0022. So I'm pretty sure I don't need a significance test to judge whether or not that was a significant improvement. I'm going to vote with no. If it takes 3 decimal places to get a number, that's generally not good. But we can ask for it anyway. This is the part of the output that SAS gives that the other programs do not with respect to all of the effect sizes. So semi-partial eta square and partial eta squares And I've noted which ones are okay to use as is and which ones are not. So like these three terms right here are okay, they're to use, but they're conditional, meaning that they are when the interacting values are 0. These two you cannot use for semi-partial R-squared because they have to be combined. They're not independent. And the rest of these are okay to use. Here's our new F-test for the two new interaction terms. Survey says p-value larger than 0.05, definitely not significant. So putting that together, the increment to the R-square of 0.0022 is not significant according to this model by these two new interaction terms. And if we get to look at what they are individually, neither one of them is significant either. So it looks like they probably aren't needed. But we can roll through the fixed effects for practice, though, because that's the most important part, is to know what to do with all of this. So intercept. I told you before that given the centering of our model predictors, that is my predicted cognition for an 85-year-old with 9 pounds of grip strength who's a dude who's never going to have dementia. Is there anything that I need to change about that interpretation now that I've added these two new interaction terms? What do you think? Has anything changed about who my reference point is for all of these predictors? Got one vote for no. You're correct. Anyone else want to vote no?
I'll go with the
It'd
correct
be- yeah.
answer.
Yeah. It's because we haven't introduced any new variables to the story. Because this is still like for an 85-year-old who's a man. So what this number for the intercept is has changed because what the model predicts for that type of person has changed given the interaction terms, but what it means has not changed. It's still the predicted outcome for an 85-year-old with 9 pounds who's a dude who does not have dementia. So if I go through and label each of these effects here as unique marginal or unique conditional, in your homework you have drop-down menus for these, so cough, cough, homework questions. Age 85 right here, is this conditional or marginal? Meaning for a specific kind of person or for everybody? And how I know that is, do I look at the rest of the list here? Is age 85 in anything else? Yeah? Yeah, that's right there. So that means this is conditional. This is only the age slope when the interaction term drops out, which happens if you're talking about men. This age 85 slope is for men. In men, for every year older you are, cognition goes up or down. This is a minus sign here. As age goes up, cognition goes down. Yeah, aging is bad for you. I wouldn't recommend it.
I'll try to avoid it.
Yeah. So in men, there's no relationship between age and cognition. That's different than what we found before. How about grip strength? Is grip strength in anything else in my model?
Yeah.
Yeah. So that means grip strength is conditional or unconditional?
Conditional.
Conditional. Conditional or simple. Those derogatory terms. I like conditional better than simple. It actually means it's complicated if it's simple. So in men, for the same reason, because grip strength interacts with gender. In men, for every pound stronger you are, cognition goes up by 0.7. Continuing on the list, the main effect of gender here, marginal or conditional?
Marginal? No, wait, conditional. because
Yeah,
it's,
two
It
things.
has to-
Conditional twice. So this is the gender difference among what kind of people? Yeah, it's not in men because this is about men versus women. But right idea. Other direction.
Women.
Men, the difference between men and women who are age 85 and 9 pounds of grip strength.
Okay.
So this is the gender difference among those kind of people. In those kind of people, women are lower by 3.7. Now how about my dementia variables here? Marginal or conditional? Marginal, yeah. They're not in any of the interaction terms. So this is the difference of how future differs from none and how current differs from none, period. Any age, any gender, anything. Last two. Marginal or conditional?
Conditional.
Ah, this is tricky. 50-50 shot.
I say both
Is there
of those,
anything
right?
else in this list that has both of these things tied together?
Oh, no.
No, it's unconditional, marginal. Yeah. That interaction term tells us how gender moderates the age slope for everybody. The second one tells us how gender moderates the grip strength slope for everybody. They're both unconditional. If they were embedded in a three-way interaction, they would be conditional on the third variable equals 0. But I decided not to do that to you this semester. You're welcome.
Thank
You're welcome.
you. It's the little things.
Yeah, I decided not to go from empty model up to three-way interactions in the same semester. But honestly, you could do it. You could do it. The original version of your homework had a three-way interaction in it, and I had taken it out. So. Anywho, let's do some practice with more positive, less positive, more negative, less negative. Okay, here's my age slope. That's in men, right? What does the interaction with gender do to it? So that's a negative age slope paired with a negative interaction with gender. So in women, the age slope is what? More positive, less positive, more negative, or less negative? And yes, I know they're not significant. I don't care about that right now. I'm just going with the numbers because I want you to know what to do with the numbers. Got one vote for more negative. Yeah, negative here, negative there. More negative is correct.
Isn't like woman 1, so doesn't have to be opposite?
We're talking about not what happens to the predicted outcome, but what happens to this age slope.
Okay.
So this age slope is
Right.
negative in men. If I multiply this number by 1 to make it for women, then it's these two numbers added together is what it is in women. So in women, it would be like minus 0.5 or something put together. So the interaction term tells you how the slope differs in the 1 group relative to the 0 group for gender. So I know that the age slope is non-significantly negative in men. I know that it is non-significantly more negative in women. Do I know if it's significant in women? I don't know that yet. It could be maybe, because a more negative slope is a stronger effect. It means the age is more bad for you if you're a chick than a dude. I know. That's because we have to spend all our time trying to dye our hair. And there's not the same stigma otherwise. Yes, I dye my hair. I'm not ashamed to admit it. Because I don't want to pick up my son from daycare and be like, oh, Grandma came to pick you up today. Because the other moms are younger than me. So I'm trying to fit in.
Just just an older mom.
I know, it's not my fault. I didn't meet the right person to have children with when I was younger. So, you know, I just scrap that plan and do something else. But yeah, I'm mom, not grandma. So yeah, age is more badder for you if you're a chick. Is it significantly bad? I don't know. Let's go find out. Here's the age slope that I asked for the women. Turns out, yeah. So here's what it was in men. That was given to us by the model. Here's what it is in women. So yeah, in women, there's a significantly negative age slope. In men, the age slope is not significant. However, those two terms are not significantly different from each other. Otherwise, the interaction for their difference would have been significant. Yes, indeedy. So this is actually a tricky situation to talk about because the interaction term means that there is no difference in the age slopes, yet how we would talk about what it is in each group, it's significant in one and not the other. So I'd probably say all of those things, potentially. Keep in mind that one thing that's going to control whether or not our age slope is significant within a specific subgroup like this is how large the subgroup is. The larger the group, the more power you have for the slope in that group. So it could be not significant for men because I don't have a lot of men or because it's not a strong effect. I'd have to compute an effect size for it to describe how strong it is in an absolute sense because this is in years of cognition. All right, 314. Questions before we call it not just a day, but a week.
No, I felt like I actually knew what you were talking about today.
Hooray! I love hearing that. Well, then I'll end on a high note. Thank you for being here. I'll see you for our last week together next week. Let me know if you need anything. Do your formative assessment.
Bye.
Thank you. Bye, everybody.